morning. Thanks for inviting me. So who got up this morning and thought, I really, really want to learn about graph theory because that stuff is so fascinating that I haven't given it like a single fucking thought since I left those dull algorithms classes in university. I'm going to assume that that's none of you because it's so entertaining and brilliant and you're all like terribly eager to learn about graph theory, even though I don't have robots or flashy things to show you. I mean, it's actually quite a tough act to follow, so thanks, Leah, for doing a brilliant job. It's going to make my job just that much more straightforward. Brilliant. All right, so my name's Jim. I work on the Neo4j database, and I'm not going to talk to you too much about Neo4j. Who knows Neo4j? Who knows graph database? It's brilliant. Those of you that don't know Neo4j, it's wonderful. It's a super duper database, and it's terribly geeky and interesting. But I don't want to talk too much about that today. I want to talk about analytics, data analytics, in particular how graph theory can be really, really powerful for both predictive and soft real-time retrospective analytics. And this was prompted by a guy called James Fowler. And James is a medical doctor, and particularly he's interested in public health. And he's been studying the flow of pathogens through communities, things like smoking and obesity and so on. And I saw James speak maybe a couple of years ago now. And I've got to say, I thought being a database geek was like the most wonderful thing because it's all like terribly computer sciencey, right? You kind of, the only people that can even come close to being as tedious as us are the C++ people, That was for you. And I really thought, I'm like, and this is really sad, I'm like one of the cool guys doing this low-level bit twiddling, and it's awesomely nerdy. And then I saw James, and he's done some amazing work on pathogens, as I said. And he used graph data to show how obesity spreads through a community. And it turns out, and his conclusion was from this data, from plotting the way the pathogen spreads through a graph, which is the kind of people of a town or city, he said obesity spreads at depth 2. Which is really, really counterintuitive, right? Because you think, fat parents, fat kids, right? That's the way obesity must spread. And it turns out, no, if you want your kids to be skinny, you need their friends' parents to be skinny. And that is wrong, right? I mean, how does that even work? And I'm like, no, James, you must be completely wrong. And he's like, well, no, fuck you, Jim. I've got the data. He didn't say, fuck you, Jim. He's far too polite. He's like, I've got the data to prove it. And I was just like, wow. And that kind of really turned my world a bit upside down, because I thought being down in the weeds of the database was the coolest place you could be. But when I learned that graph data itself in the kind of user space was so amazing, I thought, okay, I've got to learn a bit of this. So I learned a bit of this, and that's what I want to talk about today. Also going to learn about getting a clicker that works. It's one of those things, I always keep thinking I should replace this clicker, and then, there we go. Ooh. Really? That's a really odd thing. Okay, that doesn't look at all like it does on my screen. That's anyway. So what am I going to talk about? That's going to be no use to you, but I'm going to talk about imprisoned data models. So there's been an explosion of interest in the database community over the last kind of 5 or 6 years. I want to talk a little bit about that and where that's leading us in terms of our ability to be able to perform analytical operations. I then want to introduce you to a very simple graph model. It's actually the one that Neo4j uses. It'll give us the basic tools to build models and think about how we might do analysis over large interconnected data sets. And then I want to talk about predictive analytics. And I'm going to bring 2 things into play for predictive analytics. 2 things which are actually, in retrospect, quite similar. Southeast London, where I live, which is kind of a stabby part of the city. When you guys were doing your OE, you kind of avoided that bit of town, right, because it was a little bit iffy. And World War I. And I want to show how graph theory, if we could rewind time a couple hundred years, graph theory could actually accurately predict the start of World War I, given the politics across continental Europe at the time. And then I want to switch it round a bit and start thinking about retrospective analytics. So retrospective analytics for real-time kind of operations. So the kind of things that we can do in between a web request and a web response in order to help a user make a good decision, in order to maybe recommend them a good product or something like that. And we'll pick up on the retail domain for our examples there. So we've all been here. I borrowed this from your schema at work. And some of you are thinking, oh, fuck, yeah, that is actually my schema. How did he get that? And we've all been here where we've kind of, where we've kind of done the join of the inner, outer, upside down, reverse, backwards join through 17 different tables to change that flag from true to false. And I really wish that wasn't cropped, because it actually says tables meh. And most of my slides are actually memes. So AV guys, uncrop me if you can, because otherwise, like, half of my gags, I'm just going to have to like read them. And that's not a terribly good use of like 300 people's time, probably. I don't know, I mean, maybe it's a slow day in Auckland, I could do that. So we've done this, and the thing is, like, the relational data model, it's been fine. There's some really good things about it, right? So the notion of building a model and asking it questions in order to gain insight is actually pretty good. The problem is that as data set sizes have grown, we found that the relational database model has started to creak. And that's not a criticism of the databases. That's simply a side effect of the underlying mathematical model, which is based on sets. And of course, as you're doing joins through your data set, you're getting those Cartesian products, and eventually you get a join model. And I don't care how smart and clever you are, and I imagine you're pretty smart and clever. Much better, thank you. Tables, meh. That's right, that's the sentiment. At some point in your relational database, you will join. And that join is risky. And your second join is even riskier. And by the time you got to your third join, you are either incredibly brave or incredibly foolish, or maybe both. Because it's such an unpredictable kind of thing. So as data set sizes have grown, a new kind of category of databases have came out, and these are the NoSQL databases. And most of the NoSQL databases have tended to focus on complexity as being a function of size. And in that world, we have a family, a spectrum of possible data models, starting with the kind of simplest data model, the key value stores. And the data model for these guys is a hash map. So if you've got a key, you can store and retrieve a data based on that key. Great for things like, shopping baskets and so on. In fact, the lineage of this stuff comes from Amazon's Dynamo, which was meant to be a non-stop shopping basket service. Pretty awesome. These databases tend to have really good characteristics for availability and scale. They're quite impressive stuff. A little bit more sophisticated are the column stores. So where we have the data model is nested hash map of hash map. So a little bit more of an intricate, sophisticated data model. And the lovely thing about the column stores, things like Apache HBase, Apache Cassandra, is where the keys in the nested hash maps line up, you kind of get a natural index emerging from your data. So you do get a little bit more insight into your data compared to a plain KV store. And of course, the intelligentsia will argue backwards and forwards about which is the most scalable column store. It's the kind of thing that people read high scalability and get all sexually excited about it. They're all frothy. And it's like, it's HBase, it's Cassandra. Bollocks. I know, and you know, which is the most scalable column store. It's this. This is the British Museum. It's where we store all the stuff that we nicked, and it's got columns. And every time we need to scale it out, we just build another wing and put some more stuff in there that we nicked. Right? That's brilliant. And then there's these guys. So just as a side note, if any of you are slightly disillusioned with IT and you're looking for a way out, just maybe you fine balance whether you're going to stay or go, just Google MongoDB is web scale and then retire into farming. Actually, please do. If you haven't seen this cartoon, it is incredibly funny, but it may make you leave IT. So there are also these things called document databases, as espoused by things like CouchDB and MongoDB. And these things, I think, are the most familiar to us as developers because their data model is filing cabinet. I can store and retrieve documents, and I can put indexes on them so I can find them more easily. Now, there's a couple of smart guys who wrote a book called NoSQL Distilled, Martin Fowler and Pramod Sadlage, and they observed that there are some similarities between these data models. They call them aggregate-oriented models. And what that means is when you're storing and retrieving symmetrically, when you're storing a product document and retrieving a product document, if you're storing a customer basket, retrieving a customer basket, these things work really, really well. Right? They're really tuned for the storage and retrieval of aggregates. But where they work less well is when you want to dice that data around, when you want to not just look at storing and retrieving customer documents, but you want to mix customer data with product sales data and regional data and all that kind of stuff that you'd expect to do in a kind of typical analytics scenario. These things switch from being databases to being kind of compute servers. You end up having to extract your data out of the database, prison break it in effect, run it through your processing infrastructure, your Apache Hadoop infrastructure or whatever, kind of grind it through the sausage machine, and then out comes some insight. And that's fine, right? Because things like Hadoop can process lots and lots of data. But the downsides are that your data is now out of the database, and you are working not at query latency, but at compute latency. And even so-called real-time Hadoop, that could be seconds of latency, certainly not quick enough to put between a web request and a web response. And the cause of this is that people think of complexity in NoSQL typically as being a function of size. And I agree, that is certainly one component of complexity. But actually, I think that complexity of data is much more closely aligned with how uniform or disuniform the data is. And importantly, in the world we live in, how connected and interconnected, how intertwingled the data is. And you think about things like Facebook have made a gazillion-dollar business by exploiting the interconnections between data elements, not just the data themselves. And so my colleague Alistair Jones observes that we're kind of at a bit of a crossroads, a bit of a fork in the road with respect to data models. And in the left-hand fork, we've got most of the NoSQL databases. And our option there is to denormalize our data into keys and values or columns or documents, whatever it might be, and then accept that in order to gain insight into that data, we're going to have to do some processing. So it's kind of a compute-centric model, a kind of MapReduce-centric model. The right-hand fork in the road is where I find myself as a graph data enthusiast. We have a much richer model. We have a high-fidelity expressive model, which we call a graph. And in order to get insight from that model, we query it. We traverse the structure looking for information goals. So it's a query-centric model in a way similar to our SQL model, which is query-centric. And we find that model is much more expressive and much more intuitive. And I can demonstrate just how intuitive graphs are by showing you Southeast London. So this is London Tube map. Many of you now looking at that and thinking, yeah, I serve beer on near that station. Yeah, you laugh because it's true. Oh, it cropped. What if I wanted to ask questions about this side? Come on, 4-3. I mean, I formatted it just based on the broadcast standard of your New Zealand TV1 show, and now I'm being shown up. So the lovely thing about graphs is, even if you didn't know the London Tube network, and some of you may not, you intuitively know how it functions. If I'm here, whoops, where are we? London Bridge. This is where the Near4j office is in London, by the way. And I said to you, how would I get from London Bridge here in southeast London up to Paddington in northwest London, because from Paddington I can get to Heathrow? How might I do that? Well, of course, none of you are going to say, take a taxi, because taxis in London cost a small mortgage, right? But you might think, well, how am I going to do that? I can't literally just jump from here to here. You implicitly kind of know the rules, that if I'm at a station, I can only traverse to another station that I'm linked to. So in fact, a node in a graph kind of represents a mini index of illegal possible moves that you can now do. And of course, some of you who are foolish will say, well, go up here to the yellow and green line. Yeah, that guy that's laughing, he knows the joke. Go around the yellow and green line all the way up to here, and then you'll eventually get to Paddington. Key word there, eventually, because the yellow and green line's shit. And it's also full of Americans with big suitcases, like trying to get to Paddington in the slowest possible way possible. So that is, however, a legal path through the graph. It's just quite a high-cost path. Actually, I think the lowest cost path is to come down here on the Jubilee line and scoot up to Baker Street and then just do a cheeky little changeover on the Bakerloo line, just in case you're ever thinking of visiting us. And that's a lower cost path through the graph. But what's nice about that is we all intuitively have a feel for how graphs work. Graphs appeal to us as humans. They're really lovely abstractions. And so the originator of graphs was this dude, Leonhard Euler, or given the southeast London connotations, Lenny, as we know him, Len, down the pub. I don't know why I do that, but every time I think about southeast London, I do an involuntary kind of shanking motion. It's a really awkward twitch, actually. I should stop doing that. So anyway, Euler is this guy who you'll remember from university, right? And he is to us as computer science people what Shakespeare is to like students of literature. That is, he's just some random old dude that was put in our courses to make them harder and more boring. Says me, chief scientist of a graph company. Yay, thanks, Lenny. So anyway, so Lenny has this idea. So back in the day, there's this town called Königsberg, it's now Kaliningrad, and it's got 7 bridges spanning the River Pregel. And there's been like this intellectual challenge laid down. Is it possible to walk the 7 bridges of Königsberg, crossing each bridge once and only once? And so generations of empiricists had kind of tried this, right? And by empiricists, I mean idiots schlepping around the town. Like, no, I've been on this bridge before. I'll start all over again. It's like, if you really like walking around Königsberg, it's your ideal job. But for most of us, that's like nut-grindingly dull, right? This is not a good job to have. Euler's a bit smart. He's also a bit lazy. So all he does is invent an entirely new branch of mathematics. Right? He's like, I'm not schlepping around this town. I will solve this by inventing an entirely new branch of mathematics. And critically, he makes this observation. Much of the problem is nothing to do with bridges. It's nothing to do with towns and land masses and rivers and anything else. The problem is exactly one of stuff being connected to other stuff. So a bunch of the noise of the real world, Euler reduces, and he reduces this problem to its logical state, to a logical state from which he then generates an executable model, the graph theory, which he then uses to solve the problem. This is what we do as software people, right? So Euler's just kind of the first structured systems analysis guy. Why? Because he takes a bunch of real world problems. These are the things that are articulated to us by our product owners, right? Those kind of barely coherent muppets in suits who say, as a blur, I want blur, so that blur. And you're, are we not over this yet? There's a bunch of real-world noise, and what Euler does, he extracts the signal. He extracts the core of the problem in some logical representation, and then from that logical representation, a design, if you will, he creates an executable specification, just like we do when we're writing software. Creates the graph theory, and says, actually, no, it is not possible to walk the 7 bridges of Königsberg without retracing your steps. Fast forward 275 years, and we now have this rich set of analytical tools and mathematical tools and social science tools that we call the graph theory. Now, in order to use the graph theory, we do need to understand a little bit more about what a graph is. And in Neo4j, we have this thing called a labeled property graph model. And I can teach you labeled property graph model in 2 minutes because it's really simple. And I can teach it to you through the medium of nicking BBC intellectual property. So this is Doctor Who, this Doctor Who universe. It's a brilliant thing to do in graphs because it's a really wibbly-wobbly, timey-wimey kind of universe. That was for the fanboys. Can I get a who here? Time is weird in the Doctor Who universe. But anyway, this is a node in a graph. This is the Doctor, currently played by Matt Smith, soon to be played by Peter Capaldi, which will be interesting. And I can draw a graph of this universe, a part of this universe. And I can put a fact in. I say that the Doctor is from Gallifrey. And so I've got 2 nodes, I've got 1 relationship, the relationship is directed and it's named. And it reads well, Doctor from Gallifrey. It's not Gallifrey from Doctor, that would be a bit weird unless you're Yoda. It would be Doctor from Gallifrey. Okay, so we know 1 fact about the Doctor Who universe. I'll throw in some free domain knowledge here. The Gallifreyans, they're Time Lords. They've invented the ability to travel in time and space, which sounds pretty exciting, but they choose not to. They're like, meh. Time and space, meh. The Doctor, he's young and impetuous. He's like, time and space, that sounds pretty cool. I want to get out there and get stuck in. So he steals this thing called a TARDIS. Bonus points if you yell out what the acronym is. Okay, fair enough. You took a little bit too long there. That was not sufficient Doctor Who enthusiasm, really. I got snappier real-time responses for any Doctor Who nerdery from now on. So he steals this time machine, and he can now travel in time and space. In fact, if you're a super nerd, you might argue that the time machine stole him. That was a good episode. So anyway, the Doctor barrels off through the universe, and he starts putting right things that have gone wrong, because he's a do-gooder, right? And in the course of doing this, he starts to create a network of enemies. It's kind of an anti-social network. And he becomes enemies of the Daleks, becomes enemies of the Cybermen, becomes enemies of the Sontarans. I stole this slide from my mate Ian Robinson, and he put the Sontaran in because he knew I'd steal the slides, and he says, I look like one, which I think that's a bit rough on the Sontarans, in all fairness. So anyway, so there's an anti-social network bit of Doctor Who, but there's also a social network bit of Doctor Who, right? So the Doctor is quite a needy guy. He travels around with companions often. And usually those companions are human-looking because the BBC wardrobe budget is approximately 0. And up until recently, he was traveling with these guys. This is Amy and Rory. And you can see that Amy is a companion of the Doctor and Rory is a companion of the Doctor. And in fact, these guys have got their own side story going on, right? So Amy and Rory are in love. They love each other. They got married. They have a kid. The kid's River Song. River Song becomes the Doctor's wife. It's all... Okay, sorry. Oh my goodness, yes, it's New Zealand where you're 12 hours ahead and several series behind. And I know you have these things here called internet cups, as far as I understand it, but just get the BitTorrent out, boys and girls. Get with the rest of like geek society. But good call on spoilers, sweetie. Oh, back at you. Okay, so then there is the real world of Doctor Who. Don't worry, I'm not some like nut job that thinks Doctor Who is real. But there's another dimension to this graph. There is the real world of Doctor Who, which are the episodes that the BBC package. And they bring together the kind of mythological bit of Doctor Who, aliens and bad guys and planets and time machines and all that stuff, and bring it together with the real world, where you've got actors and directors and locations and the bloke that makes the coffee and the bacon sandwiches all brought together. And the wonderful thing about graphs is you can choose to bring all of this multidimensional data into your data set, and at runtime you can select which bits of it are important to you with no performance penalty. So if you want to find out just bits about the mythological Doctor Who, in which episodes did the Daleks appear, how many times have the Daleks executed someone yelling exterminate like they desperately needed a shit, you can find that out. It is right, it's like the actors who must have been terribly constipated when they were voicing the Daleks. Poo jokes don't go well in Auckland, it turns out. But you could also then roll in questions like, how many times were the Daleks detonated in some boring quarry in the English Midlands? You can bring all that kind of real-world data in. And graphs are delightful. They are the most multi-dimensional data structure you can imagine. Fold all of your facts into the graph and exploit any or all of them at runtime. And in Neo4j now, we also have like the idea of labels, so you can start to taxonomize these things. So now that we know what a graph is, and we had a few jokes about constipated Daleks, we can start to use this graph model to think about how we might predict behavior in the future, given a starting point. And in graphs, in graph theory, there are these things called local properties. This is a local property on my high street, on my local high street. And you'll love this, right? This is a shop that sells booze, brilliant, it's an off-license, and it serves Turkish, Greek, and Mediterranean food. But just in case you're in the mood for something terribly bland, it also sells English food, I notice, which is great. You walk in, I want some booze and some bland food, please. And these guys will sort you out. So the thing is, with local properties, graphs are a bit perverse. Like the big structure of a graph always seems quite important. When you see those lovely visualizations of Facebook where you can actually make out national boundaries based on graph connectivity, you always think the big picture is really important. Actually in graphs, it's small, it's the micro scale of graphs which is really important. Because things that change at the micro scale in graphs have profound implications for how the graph changes as a whole. So there are a few local properties that we should mention. The first of them is the notion of triadic closure. And you have to say that because the graph theoreticians think it's too childish just to say make triangles. But it's really interesting. In graphs, particularly graphs that involve humans, there is a tendency to make triangles. But the graph theoreticians won't call it that, it sounds too babyish. So in much the same way as the Haskell community cannot say the word monad without sounding like Harry fucking Potter, these guys do the same thing with triadic closure. Is Tony in the room yet, I wonder? So I've done this, I did this gag, I've done an A/B test on this gag, and I've done it with Simon Peyton-Jones in the room, and he giggled and was a gentleman about it, and I did it with Phil Wadler in the room, and he walked out. Anyway, here's a graph. Here's a graph taken from the South Park universe, and so you've got so it's a elementary school, kind of primary school a cartoon, and you've got this guy Kyle, and he's friends with this guy Kenny, and he's also friends with this guy Stan, and you can see the kind of tension in the graph here. You feel it in your own social networks. If you've got two friends, the chances are at some point they're going to meet, and because they're compatible with you, and you kind of like them to be compatible with each other, they're eventually probably going to become friends. It will close the triangle, it will make a triadic closure. I should stop doing that kind of voice. And you can see now that actually Kyle is friends with Stan, Kyle's friends with Kenny, and therefore Stan and Kenny become friends. There's just that innate tension in the graph. Now, also in South Park, there's this nasty fat kid called Cartman, who I have to say is a bit of a hero of mine, modulo the odd genocide he tries to commit. I kind of like his style. And he's friends with this guy Craig, and he's an enemy of this guy Tweak. In fact, there's a whole episode where Cartman does nothing other than try and mix it up between Craig and Tweak so they'll end up in a scrap. So we could try and close this triangle as well, and we could do this. We could say that Cartman is a friend of Craig, Craig is a friend of Tweak, and Cartman is an enemy of Tweak. But this feels a bit awkward, right? So you can imagine, let me try this. Hey Craig, Tweak is a total douchebag, why don't you kick him in the nuts? I can't do Craig. And Craig would be like, no, Cartman, I'm not going to kick Tweak in the nuts because he's my friend. So that's an awkward triangle, right? That doesn't feel stable. So this is notion in triadic closure of structural balance. This triangle, this closure, is structurally balanced. So Cartman is friends with Craig, Cartman is an enemy of Tweak, and Craig is an enemy of Tweak. I'm not saying this is morally superior, because what this does suggest, in fact, is that kids are bastards. But in this case, Cartman and Craig can gang up against Tweak, right? Of course, a nicer structurally balanced closure is where they're all friends. So there's two kinds of balanced, stable closures we can achieve. Friend, friend, friend is stable, and enemy, enemy, friend is stable. And this structural balance is a key predictive technique. And what's more, it's domain agnostic. This is a model of the great houses of Europe in the middle of the 1800s. And I've stolen this example from a brilliant, brilliant book called Networks, Crowds, and Markets by Ainsley and Kleinberg. This is a phenomenal piece of book. I mean, it's a thick, intimidating-looking academic tone, and you think that is going to be really, really dull. Actually, it's an amazing page-turner. It mixes graph theory and game theory. It is by far and away the best book, accidentally the best book on analytics you will ever read. It's definitely worth about 50 or 60 of your lovely Kiwi dollars. So in this graph, we're starting with a model where black arrows represent friendships, and red arrows represent enemy ships between the great houses of Europe. You can see here that this actually represents, you see, Austria, Germany, and Russia are buddies, and pretty much everyone else is at each other's throats, except for Italy, who's out on their own. And historians know this as a period called the Three Emperors League. So what would happen if we would go over this graph and start to make triangles, kind of close off gaps in the graph, see if we can make structurally balanced triangles in it? Okay, so we introduce Italy into the graph, and we make a structurally balanced closure by making Italy an ally of Germany and ally of Austria. That's nice. That's a stable closure. It's the equivalent of Kyle and Stan and Kenny being friends, although slightly more menacing, obviously, from a historical context. All right, cool. So let's do that. Let's move along, and then actually, what happens when Russia becomes enemies of Germany and Austria? Well, it's still a stable, balanced closure. It's just that Germany and Austria could now theoretically gang up on Russia. Okay, just iterating over a graph. Remember, graph theory knows nothing about these human-level politics. And then we fast forward still further on. Russia and France buddy up, which is too bad for the UK, right? And actually, it turns out it's too bad for you guys as well, because at this point, you are under the banner of the UK. We are, you can see what's coming. I mean, I talked about sausage machines earlier. You are about to be poured into a sausage machine at the Somme, at Gallipoli, and so on. This is worrying now because, well, actually, I say it's worrying. Everyone hates us, and we don't care. We're like the Millwall of history, if that makes any sense to you. Right, so that's troubling. But then what's even more troubling is this. Holy fuck, where did that come from? Wow, that's odd, right? I mean, because for a millennia, the UK has been kicking the Frenchies' ass. And now suddenly we have this thing. This is actually the Entente Cordiale, which my schoolboy French tells me, I think it translates roughly as "we surrender," something like that. Which is odd now, because this leads to an unbalanced closure, right? So there's a tension in the graph here, because the French are saying, oh, come on, Russia, we like the Brits now, they're all right. And Russia's like, nah, I don't like the Brits for some reason, I can't even be asked to remember. But the graph has got this tension in it, that something's got to give. This is an unbalanced closure. So the Russians then ally with the Brits. And then if we iterate over the rest of the graph, simply forming balanced structures, what we end up with ultimately is this configuration. This is all balanced closures. It also happens to be the starting point for World War I. Graph theory knew nothing about this. All it did was make triangles, and actually it predicted with great accuracy the low energy configuration of the network, if you like. And of course, leading on from here, you get World War I. There's another graph that spreads all the way down to the southern hemisphere here. You get a graph of the schism between the rugby codes. You get a complete social reevaluation of what it means to be a little England down under, and basically, fuck that. kind of this leads to a whole nother explosion of graph, which in turn, 30 years later, starts to reconverge when Europe decides to burn itself to the ground again. And you're like, well, we were not going to get involved in this, but fuck it, we love a fight. And you do love a fight, right? I mean, you are just desperate to get in there, fists flying. So as I said, I nicked this from a book called Network Crowds and Markets. I absolutely encourage you to get that book. It's phenomenal. There's one other local property I want to mention, and it's the strength, the strong triadic closure property. It turns out that you can not just have sentiment in your closures, likes or hates, but you can have strength of liking. I like you very much. I hate you a little. I'm ambivalent about you. And so we can bring this into our model, and we can start to look for weak relationships. And again, it's that perverse thing. In a graph, the micro things are important, and the weak things are important. And you'd expect, perversely, that it would be the big picture that was important, the strong things are important. It's not. It's the weak relationships that are important. So we can create a triadic closure like this, where we have Kenny, who's a friend of Stan and a friend of Cartman, because Kenny's quite a friendly guy, right? I mean, he's a poor kid. Poor kids need all the mates they can get. And so Kenny likes these guys both, but Stan and Cartman are kind of meh about each other. I mean, they're mates, but they're not good mates. They're kind of a weak link between them. And it turns out that this weak relationship property, the weak triadic closure property, is useful because it leads us to bridges in the network. It leads us to be able to discover connectivity between mostly separate communities. And you see this at elementary school, as we do here, where you've got a community representing the boys and a subgraph representing the girls, and there's only one link between them. It's a weak link between Stan and Wendy, because Stan and Wendy are sort of dating. Stan is not super good at dating, though. Every time he approaches Wendy, he gets nervous and pukes on her shoes. Unfortunately, for those of us in IT, this actually carries on into adulthood, it turns out. So that's not a terribly good story, is it? So you've got this notion of local bridges, and local bridges are useful because it enables you to pick apart bits of the graph. So you could be able to, for example, analyze local bridges in your organization by looking at email traffic to find who experts are, to find actually what your organizational structure is, despite what the PowerPoint slide that the MD sends around says, right? Because you can pick apart these local bridges and the graph will bifurcate. So this is a graph of a university karate club in 1978. In fact, I took this from the 1978 American Journal of Anthropology. And yes, in case you're wondering, the cold winter nights do fly by in my house. So we can use this notion of local bridges, these weak relationships, to start to partition a graph. Now, graph partitioning is an NP hard problem, but there are algorithms that you can use that will give you a probabilistically good outcome. Now, in this university karate club, there are two main nodes. There's this node labeled 1 and this node labeled 34. And node 1 is the guy that formed the club. He's a student instructor of karate. And as the club's grown, they found that they needed another instructor just to kind of keep up with the number of students that were attending. So they employed this guy here, number 34, as a professional karate instructor. And what's happened over time is that some politics have wormed their way into the club. And some people much prefer the original student instructor, and some people much prefer the professional instructor. And you can sort of pick apart this graph, you can partition the graph, and graph theory predicts that the club will split in this way. So the node shaded pink will end up forming a kind of clique or potentially even a new club around the original student instructor. The node shaded white will form some kind of clique and eventually partition into a new club based around the kind of professional instructor. And what's really interesting about this, I'd like to pay attention specifically to node 9 here. What's really interesting about this, and I've just told you how accurate graph theory is when it comes to prediction, graph theory gets it wrong. Oh my God, this is like invalidated my entire thesis, right? So what's happened here? Actually, number 9, here you can see, is far more embedded in the network around the professional instructor. It's got loads more links to people who are around that guy than he has to people in the kind of pink side of things. But when the club actually does split, the politics split the club in half actually in 1978, student 9 goes with the original instructor. Why? Because he was 2 weeks away from getting his black belt under that instructor. And graph theory can't account for that, right? I mean, it could have if we'd poured more data into the graph, but in this case, graph theory couldn't account for it. So graph theory is a brilliant way of doing predictive analytics, but the answers you're going to get are of high quality, but they're probabilistic, so don't be betting your pension on it alone. Yeah. So you can use this stuff, you can iterate over graphs, you can make great predictions, but you probably shouldn't, unless you're super clever at graph theory, be betting the house on it. So that's predictive analytics. What else might we do when we're doing graph theory? Well, we want to do retrospective analytics. We want to say, given the data that we have now, can we empower someone to make a smart decision? Can we make a smart decision? In Neo4j, we have this pattern matching notion. So we can tell the database, find me patterns like this, and get some, getting kind of millisecond timescales, some answers back from our graph data, from our interconnected data. And to do that, we have a query language called Cypher, which some people call kind of SQL for graphs. And I have some sympathy with that. It's not super SQL-like in syntax, but it is a query language designed to explore a particular data model. It's a pattern matching language, so you declare that you want to find patterns like blur in the database. And I first came to Neo4j some years ago, 2008 now, as a user of Neo4j, long before I joined the team as one of the developers. And there we go, thank you, wake up. And the second thing I ever did on Neo4j was retail recommendations. So back in the day, you remember, you guys have got the same here, right? You've got loyalty cards for your supermarkets, and as you go through the checkout, swipe your loyalty card, and some credit accrues, some points accrue in your account, and you'll get vouchers and stuff given to you, and those vouchers are trying to change your buying behavior. Now, back in the day, kind of 6 or 7 years ago, the way that worked was you'd swipe your card, and then some background Oracle job at this particular supermarket would crunch away for 16 hours. And then a couple of weeks later, some post would come through your letterbox, and you'd pick it up and say, oh, wow, that's spam from the supermarket, and you'd put it in the bin. Because back in the day, we didn't have recycling either, right? I mean, obviously now we'd be much more conscientious. And it turns out that's not a terribly effective way of changing your buying behavior. Now, what is a good way of changing your buying behavior is to be able to do things in real time. So there's this thing, right? If you wondered where the psychology students are that you went to university with and you think they're all serving burgers at McDonald's, they're not. They are in supermarkets and they are in your head. And one of the things that that psychologists know is that, generally speaking, we're not psychos, none of us, and I'm going to take a chance here. Here you go. So what the lady there, who is not a psycho, thankfully, did was, I just stuck something in her hand. She doesn't know what it is, but she couldn't help it. The protocol is I've just offered her something. She's still clutching it now. And she looked at it. You did? You glanced at it? Yeah. And it's a weird thing. Someone puts something in your hand, you look at it, and it's a business card, right? It's like, there's my email address. Yeah, big deal. Right? But you look at it, and the psychologists know this. So what they wanted to do was, as you go through the checkout, you get the vouchers printed on the checkout, and they will be put in your hand. And because you're not a psycho, you can't help it. You'll take the vouchers and you'll look at them. And as soon as you look at them, much, much, much higher chance of you acting on that voucher than if it was posted to you a few weeks later. Bang, they've got you. So what we wanted to do was say, well, we're going to look at your purchase history and make a brilliant recommendation to you right now in real time that will influence your buying behavior, because we're going to stick it in your hand and you're going to look at it because you're not a psycho. Yeah. So next time you're at the supermarket and you just grab the piece of paper and bundle it up and stick it in your pocket, think what that says about you. So we got a bunch of data, we stuck it in Neo4j. In fact, so we had kind of a couple of aspects to this data. We had this stuff at the top here, which is kind of a product taxonomy. And you can see things like we've got categories of beer, alcohol, which has a subcategory beer, which has some specific kind of beery things in it. We have some categories representing babies, and we have some specific categories around nappies and some specific products. And we have some consumer electronics in that we've got game consoles and specifically things like Xbox. And we've also got some customer purchase data. So we can see that this chap here, Mickey Smith, who happens to be a Doctor Who companion, has bought Badger's Nadger's Ale, Pee-wee Pilsner, he's bought some Baby Dry Nights, and he's bought an Xbox 360. And we thought this was an interesting graph, right? Because it shows a pattern that we're interested in. We think this pattern is a young father. Because when you're a young father, like, you buy nappies, and then by the time you've finished like doing all the screaming baby stuff, all you want to do is sit with a bottle of beer and like just shoot stuff. Fuck. Honestly, I'm jet lagged to crap, but it's better than what I would be doing back home right now, just beer. I hate being a parent. So we thought this was an interesting pattern, young fathers, and we thought if we could look for young fathers as they pass through the checkout, we could influence them. It was also pointed out to us that this might not be young fathers, this might be hardcore gamers. Which is a little bit icky, isn't it, really? So we went for young fathers because the kind of adult diaper thing, that wasn't us. So we stuck the data in Neo4j, kind of created a data set and stuck it in Neo4j. And we started looking for this pattern, and really the kind of, the more abstract pattern we were looking for was this. It's where a young father, so someone who we know is male and has a certain birth date, who's bought something to do with beer and has bought something to do with nappies. But what we were really looking for was where we thought they had not bought anything to do with game consoles. Why? Because if we spot that gap, it's an opportunity to print a voucher and say, here, 20% off Xbox for you for the next couple of days. And that was great, right? So the Oracle guys who run the Oracle DBA, we can do that. We can pre-compute the recommendation. Okay, yeah, so you don't need this cool graph technology which will do this in milliseconds in real time. You go ahead and do a massive batch job to compute it. And for once, the psychologists were on our side. They're like, yeah, so there's a thing, right? So there's a spectrum of quality of recommendation. There's a good recommendation where you find a customer need and you meet it. There's kind of a meh recommendation where you find something the customer's like, I do not care at all, because I'm a bloke, I do not care at all for cheap vegetables, right? Unless they're oven chips. Do oven chips count as cheap vegetables? Maybe. And then there's like a recommendation which you can only describe as antagonistic. And it says this: beep, oven chips. Beep, beer. Beep, Xbox 360. Beep, whatever, baked beans. It's kind of a student shop. Beep, beer. And then transaction finishes. I'm making noises. I've never made the noises before of the printer. This is a new thing for me. Voucher prints out and the voucher comes here. 20% off PS3. Fuck! I've just bought an Xbox. Just this minute bought an Xbox. Yes, sir, but the computer last night when it crunched through the batch said that you needed a PS3. Fuck you, computers. That's just irritating, right? And that actually, for the psychologist, that's troubling, because that now has not only stopped me from my buying behavior being changed positively, it's really negatively influenced what I think about the retailer. Because I just think they're muppets and they're taking the piss out of me. And no one likes to go to a muppet taking the piss out of you retailer, right? It's not your first choice. Don't quite know how Dick Smith survives, but anyway. Maybe you guys are more forgiving and tolerant. So how are we going to solve this? So we've got this idea that we want to look for this pattern, but what do we do next? Well, in Neo4j, you would simply turn that kind of PowerPoint graph into an ASCII art graph. It's exactly the same. It's just that I wrote it in ASCII art rather than writing it in PowerPoint. It's the same graph. It's a bit of a weird thing to do, Jim. Well, yeah, it's a little bit weird thing to do, unless you then realize that if you flatten this out and add the keyword, and then start to embellish, what you get is actually legal Neo4j query syntax. So the structure of the graph itself lends itself towards writing your queries. If you've drawn this on a whiteboard, if you've drawn your graph on the whiteboard, and then your business analysts are all like, well, but how do I query this? You need a very specialized tool. It's called a different colored pen. And all you do is you write the ASCII art equivalent of the graph on top of it, and the queries emerge beautifully from the structure of your graph. So here, I've actually got legal Neo4j query syntax. And what does this query say? It says, find me patterns like this. I'm interested where I've got a person who bought something that's in a particular category, where that person bought something else in a particular category, and I've introduced a category. Then I'm constraining the categories and saying the first category is something to do with nappies, the second category is something to do with beer, and the third category is consoles. And then a final constraint is where the customer has not bought anything in the console category. So it's bought beer, bought nappies, has not bought an Xbox or a PS3, and then return me the results. If any of you can do that in SQL, good on you. That's great. You are clearly one of those people who bought the book, Managing Trees in SQL for Smarties. You are a smartie. I can't do this in SQL anymore. It's too hard. In graphs, this stuff is really easy. Doing recommendations in a graph is easy and pleasant and humane. And finally, you get an answer. And unsurprisingly, it's a Doctor Who companion that pops out as an answer there. So why is this important? So we like this, or I like this. But it's not just like me and my mates at Neo that are doing this stuff. The Facebook guys have made a business out of graphs, and we thank them for that, because every time they write graph something, our metrics go through the roof. Because everyone wants the Facebook stuff, so they get Neo4j. So Facebook recently introduced this thing called Facebook Graph Search. Any of you got access to it yet? Wow, they don't like Kiwis, obviously. So Facebook Graph Search enables you to enter natural language queries and have it search your graph. So you can do things like, find me burger restaurants in Auckland that my friends like. and it will be able to return you a query not based on some arbitrary search index, but based on your social graph. Because your graph is far more trusted, your network is far more trusted than the great unwashed idiots on the internet. Yeah? Your friends, their recommendations mean more to you than my recommendations mean to you. Apart from one recommendation when I say use Neo4j, it's awesome, that is the most important recommendation. That's the most important recommendation for all of you. So Facebook do this stuff. So you can ask things like, in which New York sushi restaurants do my friends like? And so you can see here, that's a very graphy thing. So there's me, told you I like Eric Cartman. And here's my friend Andreas, my friend Michael. And they like these restaurants, iSushi and Sushi Zam, which both serve the cuisine sushi, and they're both in New York. Obviously, this graph has been simplified for presentation, because New York wouldn't be a single node, it would be a graph itself of boroughs and streets and blah, blah, blah. And probably cuisine would be a little bit more structured as well. But my colleague Max DeMasi looked at Facebook graph search. He's like, that's awesome, that's really useful. And he says that he was completely ignorant of natural language processing, and that ignorance enabled him to reproduce Facebook graph search in a weekend on top of Neo4j and make something that was more functional than Facebook graph search, because Neo4j is a general purpose database, Facebook's quite specialized. So if you're going to do this in Neo4j, of course, it might not scale to Facebook scale in a weekend. But certainly in terms of functionality, it's better than. How would you do this? Well, you write the query in Cypher. You say, find me this pattern. I'm interested where I have some friend that likes some restaurant in some city which serves a cuisine, and then we'll bind restaurant and city and cuisine to me, to New York and sushi, and give me back the restaurants. That's Facebook graph search. All you have to do is put some natural language processing in front of that to pick out the important nouns, and off you go. You can enrich that with labels. You can make sure now that you are getting people, you're getting restaurants, you're getting places and cuisines. And in fact, then you could even compact it in Neo4j. You could take that rather long query and turn it into a 2-line query. All you're saying is, find me this pattern. I've got some graph data. It's all interconnected and lovely. Find me this pattern in that intertwingled data and tell me about it. And then finally, return a restaurant. The important thing about this and why Facebook scales is, graph queries are not proportional to the size of the data set that's in the database, unlike SQL queries. Graph queries are proportional to how much of the graph you choose to explore. So in the Facebook case, we would, even though the graph is like a gazillion nodes and a gazillion relationships, we might only explore a handful of those nodes and relationships to find my friends who like sushi restaurants in New York City. Meaning that this stuff is super, super good for doing real-time OLTP kinds of workloads. You'll get answers back in milliseconds, not minutes or hours. And in fact, a lot of people who come to Neo4j for performance reasons. They're saying, I've got a query that takes minutes or hours or days in my SQL database. I bring it to Neo4j, that drops down to seconds or milliseconds. Because the graph model, the graph mathematics, does not suffer the kind of Cartesian products of sets, the join bond problem, that relational databases do. Nor does it suffer the kind of join at the application level problem that the other key value style NoSQL databases do. But Neo4j isn't just good for kind of social workloads. Neo4j graphs in particular, I think graphs are a very, very broadly useful use case. They are, Neo4j, I'm confident now, is a very general purpose database, and I'm convinced that graphs are the best data structure that I know of for doing interesting, useful analytic stuff. And so each day we find more and more people doing more different, useful, innovative things with Neo4j. But of course there is a cost. When I first started using Neo4j, I was working on a project that was going to be 5 years, a 5-year project to do a telecoms product catalog. And it was going to be a hard slog. There was a relational database in there. And product catalogs are kind of graphy, right? There's kind of things that depend on other things that can be bundled with other things. You can cut pricing deals based on if you take your mobile and your home phone from me and all that kind of stuff. And then I bumped into this guy who told me there were graphs in my data. And I'm like, no, you're an idiot. There are tables in my data. Do you not know how databases work? That guy's my boss now, which is really kind of an odd outcome. But I was like, okay, when I got back to work, I'm like, oh yeah, actually this does feel a bit graphy. Downloaded Neo4j in one afternoon, got the data in, and made my first query, which was upsell. Given the state of, given what you currently buy from us, look in the graph for what I can sell you next. That was going to come at about 3 or 4 years into the project. I did that in one afternoon. I took it to my project manager, and then subsequently got kicked off the project. Not a great outcome. I was expecting like applause and like warmth. I got kicked off the project, and it kind of realized why only much later. The guy was about to spend $10 million, sign off on $10 million to buy a bunch of database stuff, and he was a contractor on a day rate. And he was looking forward to earning that day rate for 5 years. And I'd gone to him and said, I've solved the data modeling in the afternoon. Now I reckon if we wrap a Ruby on Rails front end around this, we'll be done in about 12 weeks. But it took me a while to figure that out. So if you are a day rate contractor, please continue to use relational database technology because it will guarantee your longevity of income far better than using graph technology, which will almost certainly shorten your project timescales. But the thing that bothered me when I first started using Neo4j was I finished that thing in an afternoon. And then the rest of the evening, I was like, I haven't worked hard enough. I don't feel finished. I haven't done my normalization and then my denormalization. I don't feel that I've kind of strained my brain enough. And that was a nagging doubt that stayed with me for the first few times I used Neo4j. I was like, this is not difficult enough. I don't feel that this is therefore correct. And then finally, I got over it. I was just like, actually, fuck it. This is easy and pleasant, and now I'm going to embrace it. But it took like some effort to unlearn what I'd learned from relational modeling in order to kind of go into graph modeling. Now, to help you guys, there's a book you can get. Brilliant. It's a free book. You can go to http://graphdatabases.com, and the O'Reilly book, Graph Databases, online as a completely free ebook for you to download and use. If you can get hold of Julian Simpson, who's around here somewhere, he even has paper copies if you want to have some like bookshelf kind of trophy. In fact, especially if you go to the Auckland meetup with @BuildDoctor, that's Julian, he'll be able to dish you some of that stuff out. So, thank you so much for having listened to me. I'll be kicking around all day if you want to come and talk graphs with me, but just have a lovely day and thanks for listening.